Every generative model is really trying to answer one question: where does real data live in the vast space of possibilities? Most approaches try to model that probability directly, which turns out to be brutally hard. Score-based models take a slyer route. Instead of the probability itself, they learn its gradient, the direction that points toward more realistic data, and then simply walk uphill. It is the elegant continuous view that turns out to be the same thing as diffusion. Let's dig in. First, let's see the clever shortcut at the heart of this idea. The obvious plan is to model the full probability of the data directly. But there's a catch that has haunted this for decades: normalization. To make the numbers into a proper probability, you must divide by a constant that sums over every possible outcome. And for anything as rich as an image, that sum is astronomically large and almost always impossible to compute. This approach sidesteps the whole mess. Rather than the probability, it learns only the gradient of the log density, called the score. That gradient does not need the troublesome normalizing constant at all, because the constant vanishes the moment you differentiate. You get all the useful directional information for free. So how does that gradient actually produce a sample? Watch the walk one step at a time. First, the model learns the score, a vector field over data space. At any point, it points in the direction that makes the data more probable. Think of it as a compass that, everywhere you stand, indicates which way leads toward more realistic data. The catch is you cannot know this field in advance, so a neural network learns it, using a technique called denoising score matching. Now we start somewhere random. Drop a point down anywhere in the space, pure noise, with no structure at all. On its own, it means nothing, but we are about to let that learned compass guide it somewhere meaningful. Then we follow the score. Take a small step in the direction it points. Add just a touch of random noise so we explore rather than get stuck, and repeat. This nudging procedure is called Langevin dynamics, and it slowly carries our point uphill toward denser regions. After enough steps, the point settles in a high-density region, exactly where real data lives, and out comes a realistic sample. To make this reliable everywhere, the model actually learns the score at many noise levels, from heavy to light, which is precisely what makes it equivalent to a diffusion model. Strip it down, and 3 ideas define the score-based view. The first idea is the gradient. Rather than the full probability, the model learns the score, the gradient of the log data density, which quietly dodges the intractable normalizing constant while keeping every useful direction toward realistic data. The second idea is how you sample. You follow that gradient with Langevin dynamics, repeatedly nudging a point along the score and adding a little noise, so a random starting point walks itself into a realistic one, with no probability ever computed directly. The third idea is the beautiful unification. Learning the score across many noise levels turns out to be mathematically equivalent to a diffusion model, just framed with stochastic differential equations instead of discrete steps. Song and Ehrman's work, later unified with diffusion, gives the deep theory behind modern image generators and enables flexible fast samplers through differential equation solvers. All right, let's lock in the essentials. These models learn the score, the gradient of the log data density, and follow it uphill to turn random noise into realistic samples. Because it needs only the gradient, it dodges the intractable normalizing constant that makes modeling the full probability directly so hard. Sampling follows that score with Langevin dynamics, and learning it at many noise levels makes the whole approach mathematically equivalent to diffusion. So it is the same family as diffusion, seen through the lens of gradients and continuous time, with flexible fast samplers from differential equation solvers. If this way of explaining AI clicked for you, a whole library of it is waiting at Standarity.com. Come learn with us.